Another possible way we could measure temperatures is to look at sea surface temperatures. Now, air temperatures tend to increase and decrease a lot more on a daily basis and on an annual basis than what we see in the water. The water has high specific heat, it takes a lot more energy to warm ocean water, and as the converse of that is during periods of global cooling, it's going to take a lot more energy loss for those oceans to cool down. So we can look at sea surface temperatures and see if what we are seeing in the oceans actually match up with what we see with land-based measures. Hopefully they're consistent. Right? If they're not consistent, there's a problem with trying to infer actual climate change. But what we see here is there does appear to be sort of this upward trend in global sea surface temperatures. Not all the way up to 1 degree Celsius, but sort of in the same general direction. The difference here between the blue line and the red line, notice the red line is a little bit less squiggly. This is basically a line that tries to smooth out the effects of El Nino years. For those of you that don't know, during El Nino years, the ocean heat content tends to rise a lot more than average, typically, well, these days about a degree or 3.5 Celsius, 2 degrees Celsius locally. And so if you can sort of detrend those El Nino years by smoothing the effects, you end up with sort of less jumpy data. The blue line is just sort of the raw data here. We can look at data from the cryosphere. Some of the strongest signal that we get in terms of detection is coming from Greenland ice sheets. What we're looking at here is something called a mass balance, which is basically we're looking at whether or not the Greenland ice sheets are growing from one year to the next or declining. And so from the downward slope, you're getting less ice the following year than the previous year. They're growing, the ice is expanding. And you expect year-to-year variability. However, the Greenland ice sheet has actually been losing ice over time. In fact, if we had to stretch that another 10 years, you'd see 2012 basically drops off the chart and sort of recovers a little bit. 2012 was an extremely anomalous year for Greenland. There was a 2-month-long heat wave over the Arctic, which ended up accelerating ice loss. It's recovered a little bit, but it's still much further down than what you see here. We're down at the negative 800 gigatons now compared to the baseline. If we look at the Arctic sea ice extent, which tends to drop down to a minimum every September and reach a maximum every March, we'd see also there year-to-year variability. I think 2012 or 2013 also sort of had a minimum peak, but there's sort of that general trend of a downward trend there. If we looked at the Antarctic, where most of the ice is actually present, the signal there is much weaker. And it wasn't until really within the last decade or so that we started getting a strong signal, I wouldn't even call it a strong signal, a signal from the Arctic where that ice balance started to decline in the Antarctic as well. So stronger signals in the northern hemisphere than the southern hemisphere. And I think 10 years ago when I was teaching about climate change, I said, don't worry about Antarctica, it's going to stay frozen for a long time for various reasons. But those students come back and apologize for this. Because now the Antarctic ice is starting to disappear as well. With sea level change, this is something I also had to update this year. We see that sea level anomaly again is sort of increasing, and it's the rate of increase is sort of accelerating. So if we're looking back at the rate of sea level rise in the early part of the 20th century, it was rising at the rate of about 0.6 of a millimeter per year, so not very quickly. For the second half of the 20th century, that had increased to about 1.4 millimeters a year. Up through 2017, it accelerated again. So for this third period, we're going to get about 3.1 millimeters per year. And what I have now, based on the most recent data I've gotten, it looks like we're accelerating about 3.4 millimeters per year. And again, this is global sea level rise. If you went to a place like Jakarta in Indonesia, or if you went to a place like New Orleans, Louisiana, you'd see sea level rising a lot faster because there's more to sea level rise than just sea level. You've got land that can be subsiding, going sinking down, which makes it appear that the ocean is rising faster than it actually is. And you've got other places in the world where the tidal gauges at those locations are showing that the sea level actually appears to be getting a little bit less each year as that land is getting lifted up slowly. So data from any one particular place or one region is not going to be indicative. You need sort of a whole global record in order to pick out that global trend. Yeah.
So how many data points from how many different places do you need in order for it to be considered global?
So if you want to get sea level in a global sense, you need, and it's not necessarily data points, because if you put 10,000 data points in the US and nowhere else, you'd have a biased view. So you want to make sure that it's more important that they're spread around the world rather than sheer numbers. But still, you want thousands of locations that are geographically spread. So it's not just thousands. 1,000 gauges in New Orleans is a lot. So the key thing with climate change is not looking just at air temperatures, or just at sea temperatures, or just at the cryosphere, or just at sea level rise. You want to make sure that any kind of data you're getting is basically consistent across these different places. One place where we don't see a lot of consistency at this particular point is the amount of moisture in the atmosphere, which appears to have gone up a little tiny bit. But we're not seeing a real strong signal yet from the amount of water in the atmosphere. And that's sort of, again, sort of in a global sense, across all places, year to year. First of all, it's difficult to measure. But secondly, a lot of precipitation or moisture you get in the atmosphere is driven by global environmental conditions, and it tends not to stay in the atmosphere very long. So it's very difficult to measure. And that's not to say we don't have an increase in temperature. You end up getting a big increase in the amount of moisture in the air locally, which helps intensify storms. But we're not seeing that broad trend in the global sense just yet. So most of our indicators are also marching in lockstep. We've got this one that's not giving us good indication of protection. So the weight of evidence, just in terms of detection, you're saying, our temperature's going up, is the climate changing? The data pretty unequivocally says, yeah. There's no real compelling evidence that temperatures are not increasing in a global sense. And that's not, we're not dealing with the idea of what's causing it. It's a separate issue called attribution, but in terms of detection, we've got several independent lines of evidence, all of which indicate not only just a changing climate, but changing direction in terms of getting warmer over time. Any questions? One of the odd phenomena that we're not going to get into in this class is with climate change, we can talk about sort of a global average, but global averages are not inherently interesting. Something that is interesting is the fact that all areas of the globe are not going to warm uniformly. In fact, we expect to see greater warming in polar regions compared to temperate regions, and greater warming in temperate regions than we see in tropical regions. And this has a lot to do with how heat is transferred from the tropics to the temperate zone and ultimately up to the poles. Not terribly important in terms of the process, but what is important is that some of the places that we're seeing climate change occurring most rapidly are in polar regions. So we're going to go to YouTube University and look at a short video on climate change in Alaska. Take notes because I have a number of questions I'm going to ask associated with this video.
If we think about climate change, most of society is focused on fossil fuel combustion. But what humans release on an annual basis is just one part of the carbon cycle. Carbon dioxide concentrations also go up and down because of the actions of plant photosynthesis taking carbon out of the air, and then respiration by all living things releasing carbon back to the air. So as humans continue to release fossil fuels into the atmosphere, it's critical to know what these natural ecosystems are going to do in the future. Are they going to play a role like they do today, balancing the carbon cycle? Or in the future, might these systems release more carbon to the atmosphere, which will increase future warming?
Alaska in many ways is at the forefront of climate change because of the dramatic temperature changes that have been seen here. And it is an indicator of changes that are taking place across the whole high northern latitudes. Boreal forest extends from Siberia and northern Eurasia, and it stretches all across southern Canada all the way up to Alaska, where it's primarily concentrated in the interior. It's dominated by evergreen conifers, but there is also a significant deciduous component of aspen and birch. My particular interest in boreal forest is how the forests are changing and what the feedbacks are to climate, how much the warming and drying in these high northern latitudes has changed the fire regime, and how it's changed what grows back after the fire. 57 watts per meter squared. We estimate how much light is absorbed by the trees because that drives photosynthesis. And we also measure the carbon dioxide fluxes through time. 68. We see quite dramatic changes in the amount of area that burns every year, the intensity or severity of burning. Most of the big fire years have been in the past 10 years, with the biggest by far being 2004, 2005, and then 2009. Changes in burn severity mean that we see this greater deciduous component of the forest coming back, out-competing this conifer forest that was there before. And that feeds back to the climate system in a number of different ways. Deciduous forests grow much faster, they're more productive, so they take up a lot of carbon through productivity. Whereas a conifer forest grows slowly, incrementally through time. Another way the forest feeds back to climate is in how they reflect light. So a dark conifer forest is absorbing a lot of energy and warming the surface, whereas the deciduous forest is much more reflective and actually reflects light back to the atmosphere. So if we see this regime shift to more deciduous species, that suggests that we're not only taking more carbon out of the atmosphere, but the forests are also reflecting more light back. And those would both tend to mitigate the impacts of climate change. but I think much of that mitigation could be dwarfed by the carbon that has been stored here over centuries in permafrost soil. As that thaws, it could release an enormous amount of carbon into the atmosphere. And that's, in the past, that's been referred to as the carbon bomb.
We're inside a permafrost tunnel that was drilled in the 1960s. And what we're looking at are plant roots that grew here probably 10,000 years ago. And these roots, they look alive, but really they've been frozen since that time, trapped in permafrost. Permafrost is permanently frozen ground that contains carbon, the remains of plants and animals that have accumulated over thousands of years. What's exciting about permafrost is that deep in the soil is sort of like the outer space of ecosystems. We tend to think of an ecosystem where plants are growing at the surface, but with permafrost ground, we're finding that this carbon pool extends down tens of meters, but it's also frozen in place, so it's protected by its current climate. What we're seeing in this core, this dark brown color, is pockets of organic carbon. This is exactly a type of pool that we would call vulnerable to climate change. Right now we have twice as much carbon stored frozen in permafrost soils than there is currently in the atmosphere. In a warmer world, as the ground thaws, that carbon may end up as a big release of carbon to the atmosphere and increase future warming. So the ultimate question that we have is, once permafrost thaws, what's the impact on the ecosystem carbon cycle, and how does that feed back to climate change? This site is an experiment that we set up to actually warm up the permafrost ourselves. Each one of these boxes, as it closes, it encompasses a small atmosphere. Then we're measuring the movement of carbon dioxide in and out of the ecosystem. The first one is 55. To get a perspective of this exchange of carbon, we need to make these measurements during the day and the night, during all seasons of the year, to come up with this annual movement of carbon between the ecosystems and the atmosphere. Currently, we have computer models that predict the future climate, but these models have nothing in them in regards to permafrost carbon. So we're working to integrate the variables we measure here about permafrost into these models.
The changes that we're seeing in Alaska are not like anything we've seen, certainly in our lifetimes. So in some ways it's exciting as a scientist to be able to study it, but at the same time it's a bit worrisome.
The pace of climate change is much faster than we ever have seen in the recorded past. So what that means is there's a lot more uncertainty about what the outcome will be. Everyone wants to predict the future, which we know is impossible, but we use our scientific analysis and computer models to get a better understanding of future climate.
So why are the scientists studying the boreal forest? Your hand's not up, is it?
Yeah.
No. Why are they studying the boreal forest? As opposed to any other forest? Okay, so we have permafrost as part of it. But what else about the boreal forest?
The relationship between the deciduous and coniferous trees play an interesting role in looking at burn rates, because deciduous tend to grow better when there's more burning, but also in light absorbed and light reflected, looking at that, how it changes in the relationship between the two.
Okay, so that's a piece of it as well. Yeah.
They're rapidly changing and also are in an area that isn't fitting to get the most change.
Well, I think that's sort of the key piece. I mean, if you're going to study the effects of climate change, you're gonna wanna go to a place where you're gonna get that signal the fastest, where you're gonna get the signal the strongest. And it's not necessarily that what happens in Alaska is necessarily gonna be representative of what happens everywhere. But in terms of doing research and understanding how ecosystems begin to respond, the best way to do that is to go to a place where it's changing most quickly, so you can sort of capture those changes. So we sort of had an answer to this. How do these more frequent fires, which had occurred over the previous decade, affect the forest? And we saw that there's two things going on. As you get those severe burns coming through, you get the shift towards deciduous species, the aspens, the birches, which grow faster, which reflect more light back, so it doesn't get absorbed, it gets sort of reflected back. And both of these, because they're faster growing, they're taking up more carbon. So in this sense, you have basically a feedback within the ecosystem that's sort of dampening or slowing the rate of climate change. More CO2 is being taken out of the atmosphere, and because of the albedo, the idea that the leaves are reflecting light back rather than absorbing it and warming, that's sort of helping mitigate the effects of climate change. So what's permafrost?
Frozen dirt and organic material that stays frozen year round.
Okay, it's frozen all the time. Was it always frozen? Once upon a time, it was not frozen. However, it is now ground that's frozen year round, and inside that permafrost tunnel, that had been frozen in excess of